We are now up to the very last learning intention of the topic, which is, of course, applying logarithms to real life applications. So it's quite common to use logarithms, sorry, to calculate the magnitude of earthquakes, length of loan repayments, determining the rate of radioactive decay, population growth rates, as well as pH levels. The one you might be the most familiar with is using the log scale to deal with different pH levels. So that is quite common, particularly in chemistry and potentially biology as well. The example we're going to look at here, though, is determining the time taken for radioactive decay. So this is represented by this function. So m of t is equal to m naught times by 4 to the power of minus 0.005 t grams. So that m obviously stands for the mass in grams. And what it's telling us, it's going to decrease by 60% of its original mass. So we want to find when it's going to hit that 60% decrease in how much time. So we can see that m of t is equal to 0.4 m to the 0 as it decreases by 60%, right? If we want to decrease, then we need to be multiplying by 0.4. So substituting this into our function gives us that 0.4 m of 0, because remember this 0.4 is representing a 60% decay. And this is going to be equal to m of 0 times by 4 to the power of minus 0.005 t grams. Now, what I'm going to do is, of course, dividing both sides by m naught, okay? It's going to cancel out these two m to the 0, so my initial m values here. So I'm just left with 0.4 equal to 4 to the power of minus 0.005 t. Now I want to get t. So doing this, I'm going to take the log base 4 of both sides. So log 4 of 0.4 is equal to log 4 of 4 to the power of minus 0.005 t. So we know that this log 4 and 4 cancel out. So I'm left with minus 0.005 t on this side. Again, I'm going to divide both sides by negative 0.005 to get t by itself. And this is what it ends up looking like. Now, equating this into your calculator should give you 132.19 years. So we can say that therefore the time taken for the radioactive decay to decrease by 60% of its original mass is 132.19 years. So this is a long, long time for this particular radioactive substance to decay by 60%. I hope you all have a go at doing the final example question below. We can now have a look at the examples for our very last learning intention. So it is asking us to, of course, graph using technology this equation right here. So we've got that a to the n is 1000 times by 2 to the power of 0.7 n hectares, of course. This question is asking about insects that are plaguing a farmer's land here. So of course, to be able to draw this, we need two things, and the first one is any of my asymptote as well as my intercepts. Now it says to do this using technology, so you should graph this function here into your graphics calculator. And what we want is, of course, we want to find our x-intercept, a y-intercept if there is one, as well as any other points that we need. So firstly, I actually might find the y-intercept. So we know we can use this using our graphics calculator. So for this first one here, we can see that if we have our y-intercept, that's when my x is equal to 0. And even looking up here, if we were to plug 0 into here, this would go, this second term here would just turn into 1. So this would just be 1000 times by 1, which actually means that when my x is equal to 0, I'm actually going to have a y value that intersects at 1,000. So that's my first point, and that's my intercept here. Now, if we had a look at my asymptote here, we're not actually going to get an x-intercept at all, because this asymptote is actually when my y is equal to 0. And we know this because this here, of course, we have our equation, which is k times by a to the power of x take away c plus b. And we don't have a plus b here, so this must mean that my asymptote is at 0. We also, I guess, want to think about, in terms of this application, it's talking about number of weeks, as well as like my area, which is of course in hectares, and thinking about when you can't actually have negative area, nor can you have negative weeks. So really, when I draw up my graph here, with its really straight lines that you are absolutely going to do with a ruler, we shouldn't be looking at any other of my quadrants, because otherwise we're looking into negative weeks and negative area, which just doesn't make any sense. And of course, making sure that we definitely remember to label these. So a to the n, which is in hectares, and our n, of course, which is in weeks. So making sure that you definitely remember to label these. Of course, at the beginning here, we've got 0. And for this question, it says to estimate the time taken to reach 5,000 hectares. So we need to at least make sure on here we reach 5,000 hectares. So I'm going to go up by 2. So I'm just going to go 2,000, 4,000, and 6,000. And you are going to do this way more nicely and to scale. And remembering the other thing that we want, so that we're not kind of just drawing an exponential graph with our only point that we really have at this stage being when my x is equal to 0, my y is equal to 1,000 here. I don't want to kind of draw an exponential. I do also want at least 3 other points. So in my calculator, I'm going to obviously graph this, as I said, and go to GSolve, and I'm going to look for my y value at 3 additional points of x. So in my own graphics calculator, I've found it for when x equal to 1, x equal to 2, and when x is equal to 3. You can do any number, but these are just the 3 that I've decided to use. So I found when my x is equal to 1, my y was equal to 1,624. Whoops, probably should have done that first. At x equal to 2, my y calculation was equal to 2,639. And when my x equal to 3, my y was equal to 4,787. So I'm also going to plot this 1, 2, 3 onto here. So I'm just going to go 1, 2, and 3. And I might just do an extra point here, 4. And I can also plot these additional points onto my graph, just so I have a bit of a better approximation here. So 1,724 is a bit over halfway of my 1,000, so I think it should be about there. 2 should be about, oh gosh, I don't know, about here. And my 3 jumps up a bit, so I think that is about here. Obviously, like I said, yours will look a lot better than mine. Now I'm going to draw this and making it very obvious that there is an asymptote here, and then drawing upwards in this kind of trend. There we go. And now to actually answer my question, so hence estimate the time taken for the affected area to reach 5,000. So reading off of my graph, I think my 5,000 is about here. Oops, probably went up a little bit. And then coming, down. Ooh. That looks approximately like 3.5. So that's my approximation. So the time for this to be 5,000 hectares to be affected is approximately, we're going to say 3.5 weeks. You may get a better approximation than me if your graph looks more to scale than mine. What we're going to do is we're going to find a more approximate timeline for when the affected area reached 5,000. So of course we want to have this equation up here equal to 5,000. So I'm going to have, that 1,000 times by 0.7 n is equal to 5,000. And I'm going to solve for n, so dividing both sides by 1,000, I'd get 2 to the power of 0.7 n is equal to 5,000 divided by 1,000. So then 2 to the power of 0.7 n is just going to be equal to 5. Coming up here, as I'm running out of room, we are going to take the log base of 2 of both sides. So 2 of 2.07 n equal to log base 2 of 5. Of course, knowing that these two can cancel out, and I'll have that 0.7 n is equal to log base 2 of 5. Dividing both sides by 0.7 gives me log base 2 of 5 divided by 0.7. And evaluating this into my calculator actually gives me that n is equal to 3.32 weeks. So our approximation was actually pretty good. It wasn't too far off. So remembering, applying all of our logarithms and everything we've learned to application questions is not that hard. You can all do it. So have a go at some of the questions that are set this week and ask me any questions if you need.